If you look at all black hole imaging, you might think the photons that make a black hole's shadow simply fall in, like rain pulled into a drain. But the striking part is that many of the photons that produce that shadow never go straight down, they loop. They can execute unstable orbits, circulating multiple times before escaping or being swallowed. And the pattern of those loops, what people call the photon ring, is not just a geometry trick. It's a fingerprint of chaos governed by something as precise as mathematics, Lyapunov instability. So here's the open loop question. How can light, traveling at a fixed speed and obeying strict equations, behave like it's unstable in the everyday sense of unpredictability? Today, we'll connect that unsettling idea to a measurable structure around real black holes. To set the stage, imagine the before world of black hole physics. Long before anyone saw rings, theorists understood that in general relativity, light follows curved space-time. If you could fire a flashlight near a sufficiently compact mass, there would be directions where photons orbit the center. In Newtonian gravity, stable circular orbits exist. A planet can keep going at the same radius. But near a black hole, the photon sphere is different. It's a knife edge. Slightly inside or outside the right radius, the photon either plunges inward or escapes outward. This is already counterintuitive. The orbit is possible, yet doomed. When the Event Horizon Telescope began imaging the Milky Way's black hole, it hinted at a thin, bright feature inside the shadow, an echo of the doomed photon paths. The prevailing challenge was to explain not only the ring's existence, but why its structure is so sharp and why tiny differences in starting conditions produce the bright, repeated arcs we see in simulations. Here's the deep dive. Consider a black hole as a cosmic optical system, except the lens is space-time itself. Around a Schwarzschild black hole, there is a radius where photons can orbit. Call that radius RPH. Set a photon on exactly the right trajectory, and it stays at RPH forever. But forever is the trap. That orbit is unstable. Now think of a ball balanced on the top of a hill. If you give it exactly 0 sideways push, it stays at the peak. If you nudge it by the tiniest amount, it rolls away down one side or the other. The photon sphere works like that peak. The nudge is not a hand gesture. It's the initial angle and impact parameter, the precise way the photon threads the gravitational field. Lyapunov instability formalizes this. If two photons start with impact parameters that differ by a tiny amount, their separation grows exponentially with time, roughly like xv, where lambda is the Lyapunov exponent. That growth rate is not arbitrary. It depends on the black hole's gravity. In plain language, the black hole amplifies microscopic differences into macroscopic outcomes. One photon loops more times before escaping. Another escapes earlier, another plunges. This is why the photon ring is so thin, yet so bright. Photons that spend more coordinate time near the photon sphere cluster into narrow trajectories that radiate toward the observer. In the simplest picture, light can approach from infinity, wind around the black hole, and eventually either cross the horizon or fly away to an observer. Each additional half-orbit corresponds to a larger number of loops, and because the instability grows exponentially, there is a hierarchy. Trajectories that remain near the photon sphere for long times are exponentially less likely, yet when they do occur, they pile up into distinct ring-like features. Real black holes rotate, so the story generalizes to the Kerr spacetime, where prograde and retrograde photon orbits differ. Still, the core idea persists. Unstable photon orbits create a repeating pattern, and Lyapunov exponents set how quickly that pattern decoheres as trajectories diverge. There's also an observational twist. The shadow is largely about which photon directions miss the observer and fall behind the horizon. The photon ring is the set of directions for photons that skim, loop, and then reach the telescope. In simulations, you can literally see higher order rings, paths that loop 1, 2, 3, and more times. But due to finite resolution and radiative physics, we mostly detect the most prominent, earliest few. The fact that the ring is still present, thin, almost universal in shape, tells us that the gravitational dynamics near the photon sphere dominate the appearance. The black hole doesn't just swallow light, it organizes it into a chaotic but predictable cascade. So what's the broader implication? First, Lyapunov chaos ties together two worlds: the deterministic equations of general relativity and the practical unpredictability of trajectories under tiny perturbations. That matters because modern black hole tests rely on comparing precise structure-level predictions like ring thickness, brightness profiles, and asymmetries to data. If chaos weren't there, the ring might smear out. Instead, the instability sharpens the feature into something measurable, a map of how space-time amplifies differences. Second, photon rings are a new kind of instrument. They can constrain black hole parameters and test gravity itself, because the Lyapunov exponent and orbital properties depend on the metric. If we ever observe deviations in how quickly trajectories diverge, or in the predicted spacing and brightness of ring features, we might be probing physics beyond standard general relativity. Third, this is a stepping stone toward a deeper question. Is chaos a fundamental property of space-time dynamics, or merely an emergent behavior of how we track trajectories? Photon rings show that the answer can be probed with light, not just with abstract thought experiments. In conclusion, the black hole photon ring is not a decorative halo. It's the visible trace of unstable light orbits near the photon sphere. Those orbits sit on a gravitational knife edge, and Lyapunov instability explains why tiny differences in initial conditions translate into exponentially diverging outcomes. The ring's thin, repeating structure comes from photons that linger near the unstable orbits long enough to contribute, while the exponential separation governs how that contribution concentrates into observable arcs. So, when you see that bright curve around a dark center, you're not just seeing gravity bend light, you're seeing chaos sculpted by mathematics. If you want more deep dives into the weird, beautiful physics around real black holes, subscribe now.